In this video, we're going to talk about the variance of a random variable. And the variance of a random variable is a number that describes how the random variable varies. The bigger the variance, the more the random variable varies. So suppose that x is a random variable, which can be either discrete or continuous, and suppose that the expectation of x squared is finite. Then in this case, we define the variance of x to be, well, I'll use this notation var x. This is defined to be the expectation of x minus the expectation of x squared. So just to clarify what's going on, you're taking the random variable x minus e of x squared and then finding the expectation of that. Well, there's another way to think about this. So we know that this is the expectation of x squared. I'm using this, why did I keep doing that? I'm using this because I don't want to have to pay for notability, but this keeps doing this and I can't get this to stop and it's very annoying. Oh, wait, I think there's a, hold on. Okay, now hopefully I'll stop. Okay, expectation of x squared minus 2 times the expectation of x times x. You know, if it makes it easier, then I'll just use mu. So I'll use mu for the expectation of x sometimes. And it's the same with the bracket. Sometimes I have the bracket, sometimes I don't have it. So this times x plus mu squared. That just follows by distributing x minus mu squared, keeping in mind that x is a function. So now by the linearity of expectation, this is the expectation of x squared minus 2 mu times the expectation of x plus mu squared. Well, the expectation of x is mu, so you have the expectation of x squared minus 2 mu squared plus mu squared, so it's minus mu squared. In other words, this is the expectation of x squared minus the expectation of x squared. So there are two ways of thinking about the variance. You can define it this way, or you can define it this way, and they're both equivalent. Let me see how I can... there we go. Okay. So let's look at an example. I'm only going to do one example of finding the variance. Suppose that x has a uniform distribution on the interval AB. Well, what is the variance of x? That's the question. First, we need to find the expectation of x, and we know that the expectation of x is just the average of a and b. Now we need the expectation of x squared. And the expectation of x squared is the integral of x squared times the density function of x from a to b. So what is the density function of x? Well, x is uniform on AB, so f of x, the density function, is just 1 over b minus a. So this is equal to 1 over b minus a times the integral from a to b of x squared. And that is going to be b cubed minus a cubed over b minus a. And that simplifies to, there's a 3 in the denominator. And by the difference of cubes, this is going to simplify to b squared plus ab plus a squared over 3. So the variance of x, that's the expectation of parentheses x squared, that's a squared plus ab plus b squared over 3 minus the expectation of x in parentheses squared. And this is easy, right? It's just simple algebra. You just, that's supposed to be equals, but I just equals this, which when you simplify it ends up being a minus b in parentheses squared over 12. So that's the variance. Now notice that a minus b is, well, I guess it should be, a minus b is going to be negative if a is less than b. But the absolute value anyway is going to be the length of the interval. So if you if you double the length of the interval, then what will happen? Then the variance will be multiplied by a factor of 4, right? You can see this, because if you changed a minus b to 2 times a minus b, then the 2 gets squared, and then you get 4 times a minus b squared over 12. So the variance gets multiplied by a factor of 4. So if you multiply, in general, the interval length by c, then the variance gets multiplied by c squared. Okay. And that's a simple example of computing the variance of a random variable. Now let's look at some properties of the variance. So this first one, proposition, the variance of ax plus b is equal to a squared times the variance of x. So here a and b are real numbers. Well, this is very easy to prove. It just follows from the definition. Because while we're using the linearity of expectation, we know the expectation of ax plus b is just a times the expectation of x plus b. And let's let mu be the expectation of x. That simplifies the notation. So the variance of x is equal to the expectation. Now here I'm going to use, the variance of a plus b. I'm going to use the other characterization of expected value. I'm using the one in the definition. So sometimes, it doesn't really matter, of course, which one you use, but one of them will probably be easier than the other. So I'm going to use the first one for this. So it's the expectation of the random variable ax plus b minus the expectation of ax plus b, and that's just a times mu plus b, so this squared. And what's going to happen is you are going to get some cancellation. So this is the expectation of a times x minus mu, but the b's cancel. So you have this squared, and then you distribute this thing across, and you get an a squared, and you pull that out. So it's a squared times the expectation of x minus mu squared, and that is by definition, this is by definition the variance of x. So this is a squared times the variance of x, which is what we wanted to show. So in particular, if you have a constant, it's equal to 0. Because we can take a to be 0. And it turns out that, so this illustrates the fact that if you have something that's that doesn't vary at all, it has 0 variance. Conversely, as you might expect, if you have, here's another proposition, suppose you have a random variable whose variance is 0, then x is equal to the expectation of x with probability 1. In other words, so what does it mean for this to be true with probability 1? It means that the probability that x is not equal to expectation of x is equal to 0. Okay. So that, in other words, the probability that x is equal to expectation of x is equal to 1. And that's not necessarily saying that x is always equal to ex. So for instance, you can have a constant. It could be that x is constant except for 2 points. So maybe x is a continuous random variable, but it's not equal to expectation of x at 2 points, but everywhere else it's equal to expectation of x. Then the probability that x is not equal to expectation of x is equal to 0. Okay, so now let's prove it. Proof is a bit tricky. So first, let's C be a positive number. What it suffices to show is that the probability that the absolute value of x minus expectation of x is greater than C is equal to 0. Okay, why? Why does it suffice to show that? Because then we know that the probability that this is less than or equal to 0 is 1. Right? Because we suppose that we know that the probability of the absolute value of x minus expectation of x is greater than C is equal to 0 for all C greater than 0. Then with probability 1, this random variable, the absolute value of x minus expectation of x, must be less than or equal to 0. But we know that this random variable, the absolute value, has to be greater than or equal to 0. So then the probability that you have this absolute value is equal to 0 is equal to 1. But that's just saying, if the absolute value of x minus ex is 0, that's just the same as saying that x is equal to ex. Okay. So because of that, let's define a random variable, which is 1 with this subscript. And this is a random variable, which is, it takes the value 1 if x minus, so we have a little x, minus the expectation of the random variable x if this in absolute value is greater than c and 0 otherwise. Well, then it's easy to see that the absolute value of x minus ex squared is greater than or equal to c squared times this random variable. It might take a bit of time to see why this is true, but it's because the thing on the left, so what happens when you plug in a little x into this? This is greater than c squared if the absolute value of little x minus ex is greater than c, and it's greater than or equal to 0 if the absolute value of little x minus ex is less than or equal to c. Right? Because we know that it's always going to be non-negative. But if the thing inside is greater than c, then of course the thing inside squared is going to be greater than c squared, because c is positive. Okay. So we have this, while if you compare that to this function, this by definition is 1 if the absolute value of little x minus ex is greater than c, and it's equal to 0 if this is less than or equal to c. So by definition, the left-hand side is greater than or equal to c squared times the right-hand side. The first function is greater than or equal to c squared times the second function, I mean. Okay. Now how do we use this fact? Oops. This fact. Well, we are supposing that the variance of x is 0. So we have 0 is equal to the expectation of the absolute value of x minus ex squared. Right? That's just the variance of x. And we know that this is greater than or equal to c squared times the expectation of the other random variable. And just to be clear, we know this because if you have two random variables, x and y, and x is always greater than or equal to y, then the expectation of x is greater than or equal to the expectation of y. That's just a fact about, it basically follows from the definition of the expectation. All right, now what is this? This expectation. Well, this random variable here is a discrete random variable. Right? This is not a continuous random variable. This only takes two values, 1 and 0. So the expectation of this is equal to 1 times the probability that the absolute value of x minus ex is greater than c, plus 0 times the probability of the other event happening. Because this is from the definition of this random variable. Well, this is equal to the probability that the absolute value of x minus ex is greater than c. So we get that 0 is greater than or equal to c squared times the probability that the absolute value of x minus ex is greater than c. Well, we know that c is non-negative, so therefore, it doesn't actually matter that what c is. We just know that's not 0. So therefore, the probability that x minus ex, the absolute value, is greater than c must be 0. And that's what we wanted to show, as we explained here. So that's the proof. So this explains what happens when the variance is 0. If you have a random variable with variance 0, then it's constant almost everywhere. Okay, a few more properties of variance. Well, a useful fact that we'll use from time to time is suppose that you have a random variable x and it has mean mu and variance. Well, the variance is non-negative. And so we can identify it using the notation sigma squared, where sigma is the square root of the variance of x. Okay. So this is just a notation. Then let y be the random variable x minus mu over sigma. Then, well, by the linearity of expectation, the expectation of y is equal to 1 over sigma times the expectation of x minus mu. Well, that's just 0, because the expectation of x is equal to mu. And what about the variance of y? Well, we've seen what happens. So y is equal to this constant 1 over sigma times x minus mu, which is 1 over sigma x minus some constant, mu over sigma. And we've seen, so this is in the form ax plus b, the variance of y is equal to 1 over sigma squared times x, times the variance of x. But the variance of x was sigma squared, and so this is just sigma squared over sigma squared, and that's equal to 1. So what we found is that whenever you have a random variable with mean mu and variance sigma squared, you can always normalize it in some sense. Normalize means you kind of adjust it by forming the random variable x minus mu all over sigma. This is going to have mean 0 and variance 1. By the way, another term for this square root of the variance is called the standard deviation of x. So let's apply this fact to the normal distribution. Suppose that x has what's called the standard normal distribution. So it has density function f of x equals 1 over the square root of 2 pi times e to the minus x squared over 2. Okay. Then the expectation of x is equal to the integral from minus infinity to infinity of 1 over root 2 pi x e to the minus x squared over 2 dx. But since this is an integral of an odd function, this integral is equal to 0. Technically, one thing we need to check is that the integral from 0 to infinity and the integral from negative infinity to 0 both exist. Right? But it's easy to check that they exist. Okay. So that's the expectation, but what about the variance? Well, the variance of x, in general, it's the expectation of x squared minus the expectation of x in parentheses squared. But we know that the expectation of x is 0, and so the variance of x is just the expectation of x squared. And this is by definition the integral from minus infinity to infinity of x squared times f of x. So you get 1 over root 2 pi times x squared times e to the minus x squared over 2 dx. I'm going to skip the steps because this is really just calculus. But the idea to do this, hopefully we recognize, use integration by parts. And it turns out that if you use u equals 1 over root 2 pi x, and dv equals the rest, x e to the minus x squared over 2 dx, then you end up getting that this integral is equal to negative 1 over root 2 pi times x e to the minus x squared over 2, evaluated from minus infinity to infinity, plus 1 over root 2 pi times the integral from minus infinity to infinity of e to the minus x squared over 2 dx. Well, this, from the fact that f is a density function, we know that this integral is equal to 1. And it's easy to check that this integral is equal to 0 because what happens is the exponential term goes to 0 faster. What am I saying? Let's see. Yeah, you have an infinity times 0 indeterminate form, but you can write this as x over e to the x squared over 2, and then the denominator goes off to infinity faster, right? You just use L'Hopital's rule and you check that you get 0. So you get 0 plus 1, which is equal to 1. And so this random variable x has expectation 0 and variance 1. Okay, so x, we would say, has normal distribution with mean 0 and variance 1, and that's how we write it, like this. So this tilde means that x has the distribution on the right. Normal with mean 0 and variance 1. And we've seen, therefore, that if we define y to be sigma x plus mu, then the expectation of y is equal to sigma times the expectation of x, but the expectation of x is 0, so it's 0. And the variance of y is equal to sigma squared times the variance of x, but the variance of x is 1, and so y has variance sigma squared. And not in this video, but maybe I'll make one in the future where we go over the density function of y, and that has what's called a normal distribution. And we've seen now that we have an interpretation of hold on. The expectation of y is equal to sigma times the expectation of x plus mu. So 0 plus mu, which is mu. There we go. So now we have an interpretation of mu and sigma squared. Mu is the mean of y, and sigma squared is the variance of y. Okay, that's all I want to say about this video. In the next video, we'll talk about standard deviation, and then we will talk about the covariance of two random variables. Thanks.